Where's my clicker? So we left off. Oh, is it anybody's birthday by any chance? That was, yeah, sure. It was 116. We're at the part of the playlist where it's whatever 116 students voted on. I took the top songs, and anyone that was too ridiculous, I had to remove. There were some that were just too bad. But birthday song was in the top 10 of songs they voted on. So I'm like, well, I'll put it in the playlist, and hopefully it plays during somebody's birthday, and they'll be all happy about that. But tomorrow's whose? Oh, I don't know if I'll be lecturing tomorrow. Maybe that was for him, though. So let's talk about rainbow tables. We kind of missed this last time. We were talking about all of our attacks and hashes. This is 3:12, right? 4 o'clock? Okay. So we were talking about all the attacks and how we're only going to store hashed passwords in our database. And then if somebody has access to the database, even the sysadmins or developers, whoever has access to it, or an attacker who gets a SQL injection attack or any other attack where they can access that data, we don't want them to be able to recover your password. We still don't want them to be able to access your account. That's very important. We want that level of protection. We expect that level of protection these days. Because you see headlines all the time, or maybe you don't, depends on what news sources you're looking at, that some major corporation had a database leak. Somebody got into the database and leaked millions of people's information, and it's all out there on the internet. But when you see those headlines, there's one thing that's notably missing from them. Whenever you see a database breach like that, or at least in almost every case, I should say, some companies don't do what they're supposed to. Whenever there's a breach like that, you never see in that article usernames and passwords were recovered by the attackers. The attacker has millions of people's passwords. It'll say attacker has millions of people's credit card information, social security numbers, home addresses, email addresses, all that personal information. It'll never say the attacker got your password. The attacker got everybody's password. It doesn't happen. Because we're storing hashes, and even with the hash, they can't recover that password. Now, they can launch these attacks after they attack the database, but they're not just getting millions of people's passwords. They're not getting anybody's password who has a strong password. Yeah?
Is credit card information just stored?
Nope. Kind of. So we'll talk about this next week in more detail, but credit card information should be encrypted. It can be encrypted, or sometimes maybe it's just not even encrypted. You can encrypt it, but the idea with encryption is that if you're encrypting something, you want to be able to decrypt it at some point. If you're storing your credit card information in a company's database, it's because you want them to use that credit card. Like, they actually have to be able to access the credit card number again. So they can store it encrypted, which is one level of security to be able to hide that. But if somebody has access to your database, somewhere sitting right next to that database, around the database, probably on the same server, is the encryption key. They're going to get the key and decrypt it and get that information. And we can't really prevent it against that because the company has to be able to recover your actual credit card number to be able to use that credit card number. The same isn't true with passwords. The company never, any organization never actually has to know your password. Ever. Ever, ever, ever. Nobody has to know it. But if you make a purchase, they need your credit card number because they need to send that to Visa or MasterCard to be able to actually process the transaction. So they actually need to recover the numbers themselves. So there's a big difference there that we can't protect other personal information the same way we protect passwords. Okay, so we saw our brute force attack. That's a 116 question. So we saw a brute force attack. We talked about dictionary attacks, but there's another type of attack that's really scary that I wouldn't have had time to talk about last time. So let's talk about it now where I can do it justice. A rainbow table attack. These ones are spooky, but not anymore because we're going to salt our hashes. But why do we salt them? Well, one big reason is rainbow tables, and I'll talk about what salts are too. You're not expected to know that quite yet. But rainbow tables, the way this works is when an attacker recovers your hash and they're going to try brute force or dictionary attacks, and they're like, you know what, those attacks are just too slow and too inefficient. So what they started doing is developing rainbow tables, which these tables are tables of hashes where what they do is take a guess for a password, they hash that guess, then they take that hash and put it through a function that turns it into something that could potentially be another guess for a password, and then they hash that. And then they apply the function to turn that into another guess, then they hash that, then they apply the function again, turn it into another guess. They do this over and over and over, millions, maybe trillions, a lot of times. Millions, billions, however many times they want. That's one of the parameters they can adjust for these tables. But they do that a whole bunch of times to build what we call a chain of guesses and hashes. So each guess is a potential password that they're trying to guess, and the hash would be the stored hash of that password. And then they only store the first and last, the ends of this chain, the first guess and the last hash. Those are the only two things that they store, and that represents millions, billions, trillions, I don't know how big these things get, of guesses of passwords. And then they do this millions, billions of times to generate lots and lots and lots of chains of guesses of passwords. And then for each chain, you can store millions or billions of guesses in just two values that you have to store. And you create tons of those chains and have this huge rainbow table with lots of chains. And you can have lots of guesses stored in this table, which can get huge. These can get in the order of gigabytes of rainbow tables. And I'm told, I haven't actually tried it, but you can go and download these rainbow tables. You can just find them and say, here's your rainbow table. So these things take a long time to compute. They take up quite a bit of storage, but the trade-off is that attacking a hash is much, much faster. So what you do when you want to attack a hash, and you have this rainbow table that has pre-computed tons of guesses of passwords, got like quadrillions, quintillions of guesses. What you do is take the password, hash it, apply the function, hash it, apply the function, do the same thing you did to generate a chain. Go through that same process until the hash matches one of the endpoints of one of your chains. Once it does, you know what chain contains that password. You go to the beginning of the chain and go through your process again. Beginning of the chain and just go through until you find the hash that matches the password hash that you're trying to crack. And you back up one step, that's the password. Or at the very least, it's a value that will hash to the same value, which is effectively the password. It could be a hash collision, but it's still the password. With these, the downside of cracking a hash, which is it takes a long time, it takes a lot of processing power just to crack one single hash, all that's eliminated. You throw it at your rainbow table reduces that time significantly because you're doing millions or billions of guesses every time you do a single guess. You leverage your CPU power significantly with these things. So passwords were being cracked like fast. It's bad with these things. So we have to get rid of these, and our answer is salting. So with salting, instead of just you register with a username and password, we take your password, we hash the password and store a hash of the password. That's how we've described it so far. That's not quite enough because a rainbow table is going to rip that hash to shreds in a matter of seconds, maybe even milliseconds. So we have to do something a little bit different. We're going to add a salt. So before we hash that password, we're going to generate a long random value called a salt. And we're going to append this salt to the end of the password and then hash it. Then we store the hash and the salt in the database. And hopefully the lecture question was fair enough yesterday. I kind of said it as the question was up. You store the salt too. But you store the hash of the password, the salted hash of the password, and the salt. The salt is stored in the database in plain text. And then next time you get a password for login, you take that hash and salt out of the database, you append the salt to the end of the password, hash it, and then if the hashes match, you're authenticated. The user is authenticated. So what this does is, well, one, it doesn't add any entropy. It still takes just as many guesses to guess your password as it used to. So we don't actually add any entropy. We don't add any like raw security in the form of entropy because the salt is stored in plain text. So we don't add anything there. A dictionary attack, a brute force attack, they're still going to take just as long, maybe just some negligible amount longer from string concatenation, I guess, but nothing too intense. Well, it's probably, if I'm an attacker, I'm going to do that at the byte level. So byte array combination. But we're going to, so everything else is the same. Our other attacks work the same. But guess what happened to those rainbow tables? Completely useless. So the idea that you're taking a hash and then applying some function which turns that hash into your next guess, well, the chances of that guess ending in exactly your salt is next to zero. You're going to generate these salts to be pretty long values. It's going to be next to zero that those guesses are actually valid guesses with this salt. And every single user is going to have a different randomly generated salt attached to their account. So when you want to attack a password, this rainbow table is completely useless because most of the values in your chains don't contain that salt. Just throw away the rainbow tables. They're useless these days because everybody's salting their hashes these days to get rid of that attack. So we want to salt our hashes to get rid of that attack, or else we're pretty vulnerable to these things. When you store the salt, do you hash it? No. Vlad, I think me and Vlad tied on that one. He might have beat me by a millisecond. No, you don't hash the salts themselves. The salts are public for everybody to know. If somebody has access to the database, they have access to your salt. They know what your salt is. And that's fine. Salts, we can't use salts to add entropy. It's fine for them to be out in the plain, out there in the open, because they don't add anything anyway. There's no benefit to salts except eliminating the rainbow table attacks and a few other attacks that I'm not familiar with that salts prevent. Salts make it a lot harder to execute. So the rainbow tables, you would have to build a rainbow table for a specific salt value. You could still do that. It could be part of the function that takes a hash and turns it into the next guess. But if you're building a hash table just to crack one specific hash, really defeats the purpose of pre-computing. Really defeats the purpose of pre-computing all those values to be able to save time later. If you're building a hash rainbow table for just one single hash value that you're trying to crack. Doesn't work, not useful. And or hoping that, well, I'm going to hack this database. I hope somebody has this salt because I got this big rainbow table I built with that specific salt. Really renders them useless. Does not add any entropy. Salting does not add entropy. So your weak password, it's still weak even if it's salted. And we talked about bcrypt last time. So I'll talk about bcrypt a little more. So when you register, you're going to take that password, generate a random salt, append the salt to the end of the password, hash that's your salted hash, store that and the salt in your database. Then when somebody wants to authenticate, you're going to get that password, pull the hash and salt out of your database, append the salt to the end of the password, hash it, and check if the hashes match. If the hashes match, they're authenticated. Oh, I thought I had one more slide on that. And use the bcrypt library. Bless you. This is one where you are allowed to use the library, and I expect you to use the library. Bcrypt is pretty standard across the industry. Like this is the one we use for hashing. It's one of those things where there's not too many choices. That everybody seems to be using the same thing, which is nice. I like those things, personally. I don't like having 100 choices anymore. We always have so many choices. But bcrypt, you'll probably use this in your career some other time, too. You're going to use it in this class, too. Or you don't have to. I mean, if you want to do this all manually, go for it. But bcrypt, everything that we've talked about with salting and hashing is like 2 lines of bcrypt. So import the library, get it installed in your app. Bcrypt will generate the salt in one method call. It'll hash your password with the salt in one method call, which you can do in one single line. You can hash the salt and then hash the password and give it the salt all in one line. And what bcrypt does is give you one single value that contains the salt and the hashed password. So you have one thing that you're going to store in your database, and then you pull up that database when somebody's trying to log in. You give it, I think it's check password is the bcrypt method. You give it the plain text password and the salt and salted hash, that one single value that you pulled out of your database, and bcrypt will do all the things. It'll extract the salt from that one value, extract the hash, append the salt to the plain text password, hash it, and then check the hashes. It'll do all that for you. So just use bcrypt. We don't have to re-implement our own hashing algorithms. We don't have to do any of that. Just use bcrypt. This is one case in the course where I'm like, just use the library. It's too far removed from like HTTP and web stuff that let's just use the library. Yeah. XKCD is always. I hate when there's so many competing standards. Yeah.
So if you ever lose the salt, you're done. Like you can't never verify the user's password again.
Yeah, don't lose the salt. If you lose the salt, yeah, you're screwed. You'd send a message to the user and say, oops, something went wrong. Click here to reset your password. Because you can't do anything. Because your salts are going to be long enough, big enough that you shouldn't be able to just guess them. Like we don't add entropy because we store them in plain text in the database, but if you lose the salt, now you do have entropy. You have to guess that salt, and it should be large enough that you can't guess it. Yeah, highly recommended. This is one of the highly recommended where if you don't take this recommendation, I don't really even know how you're going to do the assignment. I mean, I guess, well, I shouldn't say that. You can, as long as you pull in a hashing library, you can still do it. And you can generate your own salts and stuff. Actually, you could do it pretty easy. But bcrypt, it's there for us. It's something you're going to use if you ever do this stuff again in your career. Let's just get used to using bcrypt. Where do I want to go from here? Let's do... I fixed my Java code. I swear, by the way, that this code worked before. This is the second time it's done this to me, actually. This code worked before, and then one time it stopped working because the method I was using, they removed it from Java because they like doing that to me. Me specifically. But they like doing that. They like removing features from Java. So it broke. And now it broke again in the middle of lecture last time. It's my fault because I should have tested it before lecture. But I'm like, I know this code works. I've just used it last semester. But I fixed it, and the fix is really awful. I had to look online how to do it, and I hate it. But it works now. So let's do the demo I was trying to do last time. I'm going to hash. I need a... Oh, I'm always hesitant to ask this because... I'll get dumb suggestions, but I'm fine if they're dumb, I guess. I need a 5-letter word. I'll use hello for my example right here, but then I need another 5-letter word for the next thing that I want to do. So I'm going to calculate the hash of hello. Well, I already calculated it because I did test this before I lectured today. And here's my hash of that. And if I also use my Java code, I'm going to compute the hash of hello just to prove. Let's comment this out for now. And I'm going to use no salt here. I'm going to compute the hash, and it's going to be the exact same thing. I'm using SHA-256. SHA-256 is SHA-256. It's a concrete, well-defined algorithm. It doesn't matter what language or how it's implemented. Well, like the implementation details don't matter as long as you are implementing the algorithm. So this website, which is probably using JavaScript, and my code, which is using Java, it's going to give you the same thing. It's going to give you the same value. So I'm just using SHA-256. This message digest, this is part of Java. It comes with Java. And then that gives us a byte array. And for some reason, converting a byte array into the hex values is where things really went wrong. I was using base 64 before. I'm tripped up because I swear I used that before, and it did give me just the hex values of the string, which doesn't make sense in hindsight. So I don't know what I was even doing, which is probably part of what went wrong. But this mess is going to convert that byte array into a string of hex values the way we would expect. Pass W. I'll go with pound or stoopy. I mean, 2 of the 3 suggestions are just not 5-letter words that you force to be 5-letter words. I'll take the one that's actually a 5-letter word, pound. So I'm going to hash, what? Was that suggested? Okay. Oh, I didn't even see that one. I didn't even see it. So I'm going to use... So very importantly, when I go into my code, I'm not going to type the string Jesse at all. It's important here. We're going to run a brute force attack. And I'm going to generate a salt as well. This is a very calculated method. Generating a salt is very scientific. There we go. Oh, I got one. I went a little too aggressive on it. Hold on. It's like a good salt. Let me get rid of white space. I don't know if that'll mess something up. But a nice long random thing. And I'm going to copy this. And this is my salt. So I'll store this in plain text in my database. And it's really long, really hard to guess, random thing. I'm going to append that to the end of my password. And I'm going to compute the hash of that. So if I'm an attacker, I get the salted hash, and I get the salt. So I have the salt, and I'll have the salted hash, which will be this value right here. I'm going to run this neat little method called brute force attack. Now, nowhere in here did I type the string Jesse into my code. I didn't know what that was before. I feel like a magician. There's nothing up my sleeves, no tricks here. I'm going to run this thing. Oh, this actually isn't going to work, is it? No, yeah, maybe it will. Yeah, because it should. No, I have the wrong alphabet here. Upper and lowercase alphabet. I was testing the wrong alphabet. Let's rerun this. I'm going to run my brute force attack. What it's doing is just guessing every possible string that can be constructed with the alphabet that I gave it, which is any upper and lowercase letter. It might take a little bit of time. My algorithm is pretty dumb. It's just straight up testing every possible combination. It's not a dictionary attack. It is a true just brute force attack. So it'll take a little bit for it to go through all of these. But while it's doing that, my brute force attack, first of all, I have the dictionary, so I gave it upper and lowercase letters. Or we could give it the full alphabet, which is all numerics and special characters included. I'm going to initialize the salt. If you just call it without a salt, hopefully I passed the salt. Yeah, salt. So I gave it the salt, a character set, and the hash that I'm trying to break. It's going to use recursion, because of course, we like recursion. And it's going to go through every prefix that can be constructed with those characters, test the hash. It's going to compute the hash with that salt, compare it with the hash value I have, and if they're the same, that's my password. I've cracked that password. If not, go through each character, build new prefixes, and test every single character, every single string of that length that can be built by this alphabet. And I chose 5 specifically because it takes a decent amount of time, but not so much that we can still get it in lecture. It'll still be longer than I remember. Maybe this new compute hash. Actually, you know what? Yeah, this is going to be really slow. This is slower than I want it to be because I'm not using string builder. This is the warning that it's giving me. I'm building a string in a loop with concatenation. I didn't think that'd give me too much of a performance hit. But we're going to sit here and wait, damn it. We're going to get there. But the big emphasis here is my brute force attack works even when the salt is ridiculously long. I don't care what this salt is. It's plain text stored in the database, so the attacker is going to have it, and it doesn't add any entropy. My brute force attack is still going to work, even though if this were a password, you'd never crack that password. Well, I would never crack that password. But we're going to get this thing cracked. Hopefully. It's making me nervous now. I don't want to do 4-letter. I can't give up. We're cracking this hash. Question?
What language do hackers usually use to do dictionary?
I don't know. I don't know. I'm not familiar with them to ask them, but probably. Actually, I do have a better answer than that. So with cryptocurrencies being a big thing now, there's a lot of hardware accelerated hash generators to be able to do Bitcoin, things like Bitcoin mining, any coin mining. They're using those these days, I would guess at least. For Bitcoin, the whole idea is that to mine coins, you have to compute hashes really fast. So using that technology to crack passwords just makes sense. And they do, like, they'll have thumb drives where it's all hardware that will compute it, because hardware is faster, even C, like hardware is the fastest thing we can get. So they have hardware that's going to compute the hashes, and then they write some code that's going to interact with the hardware. Things making me nervous, but unless we see testing all strings of length 6, we're not completely sunk yet. Let's get the slides ready while we're doing that. I don't have many slides on auth tokens. Really not much to say about this. I think it's a pretty straightforward concept. We'll revisit that. Revisit it after auth tokens. Okay, so this is the next step. This is the last step you need for LO2 on homework 4. And after this, the rest of the homework except AO3 is on the table. AO1 and AO2, there's no really new concepts. It's just now that we have authentication, let's go revisit some of the things we've done in past homeworks and make them cooler now that we have authentication. So AO1, authenticated chat. Instead of having random usernames for each user, actually use their username that they've authenticated with. And if they're not authenticated, don't let them chat. And AO2, cross-site request forgery tokens. Before, we had this vulnerability where an attacker could just make a request to your site, get a valid token, and then use that token in the attack that they're going to launch. Well, now we're going to associate tokens with user accounts. So if somebody sends a message, you're checking their account and then making sure that that token that they're sending is associated with that account and getting that extra layer of security with that OAuth token, or OAuth tokens, cross-site request forgery tokens. So both of those are on the table as long as we know what authentication tokens are. And then AO3 will take the better part of next week and part of the following week. As I mentioned before, it's one of those topics where I have a lot to talk about in lecture, to talk about how it works. But when you actually go to implement it, it's not too much. It's something where I want to talk about the background a lot. But when you go to do it, it's getting, not necessarily libraries, but it's getting other code to do the work for you, most of the work for you. I'm not crazy enough to have you go through the low-level details of HTTPS. I've considered it, but it's just too much. So here's our overview of how you use the internet when you log in. You're going to register for an account. When you want to log in, you authenticate your username and password, and then you're authenticated. And then that request, when you send your username and password, that request is authenticated. But remember, HTTP is stateless, so what we have to do is send our username and password on every single request every time we want to do anything that needs authentication, which if you're using most apps, that's like pretty much everything you do, you want to be authenticated. Any action you take, especially if you're sending information, like sending a message to social media, you want to make sure that's authenticated. You don't want anybody to be able to send those for you. But I don't know about you, I don't want to type in my username and password every single time I want to do anything ever. I'm not going to do that. I don't want to use those sites if that's what they're going to require from me. I'm not sending my username and password on every single request, or rather, I'm not typing them on every single request. If it happened in the background, I wouldn't be too concerned. I would, but for different reasons. So instead, when we authenticate, the server is going to issue an authentication token to us. This is a randomly generated token that it's going to set as a cookie. This is the reason why we learned cookies on Monday. So the authentication token is going to be generated, set as a cookie, and this token, I'm getting ahead of my slide with the cookie thing, but this token needs to have enough entropy that it can't be guessed. This token is going to be the way that we verify this user. So if we get another request, whenever we get a request that needs authentication, we're going to check the authentication token, and if that's a legit token, we're going to treat that user as authenticated. So we need these tokens to not be guessable. So in general, we like our 80 bits of entropy. We should have lots of entropy in these tokens, and the user's not involved here. The user doesn't have to remember these like passwords. So we can just crank up the bits of entropy as much as we want. So at least 80 is a good rule of thumb. Make sure you have enough entropy that nobody can just guess, brute force guess these tokens until the site says, oh, hey, you're so-and-so. We don't want that happening. So lots of entropy in these things. And then we're going to associate a token with the user. So somebody logs in, we generate a big, long, random auth token for them. We associate that token with the user, and by that I mean go into your database, store that token along with that username. So wherever you're storing you can do this with one database for homework 4, by the way, for the users, and another one for chat. But your user entry in your database can have username, hashed salted password plus salt, and then their auth token as well. So we're going to associate the token with the user by adding that token to our database in the record for that user. Now we get a request that needs authentication. We're looking for that cookie with the token in it. We read our cookie. It's got a token. We check that token in our database. So we look up what user is associated with this token. Now, the server issued these tokens, and they have 80 bits of entropy or more. So we are going to assume that these tokens are not faked, that they're not, that they are actually who they say they're going to be, or else they couldn't have guessed this token. They wouldn't have this token if the server didn't give them the token. So we're going to use this to verify users without their password by saying, well, I gave this token to a request that provided your username and password. Now, we won't actually know that because HTTP is stateless, but we're going to make that leap. We're going to say, if you have this token, I'm going to look it up in my database, and yep, this is a token that I issued. Therefore, and I issued this token to somebody who authenticated as this person, so therefore you must be, like you really should be that person, and we're going to treat them as authenticated as that person with the assumption that if they possess this token, they must have authenticated in the past. They must have authenticated with this server because there's no way they would have this 80-plus bit entropy token if they weren't authenticated by this server. Yep.
Websites request just all the cookies on your browser, or
No.
No.
Nope. Yeah. Can other websites just request all the cookies on your browser? Nope. And that's what we're talking about with the the same site stuff, we don't want these being third-party tokens, third-party cookies, where they're sent on every single request, because then any site can request. So any site can request your tokens if your same site is set to, always? Always or lax? I think lax is the default, and then always is always send them. So if your same site is set to always on your cookies, then any site that makes a request to your site, it's going to send those. Oh, I'm saying this backwards, ain't I? It's going to send those cookies, and then they can get those cookies. But since we're going to be careful about how we handle these cookies, we're going to make sure they're not sent to third-party servers. No, they would have to get the JavaScript injected into that site. Yeah, it's a little more complicated, but we're going to make sure that they can't be sent to third parties anyway, regardless of how they set it up. So you do have to store these servers, and these servers are as sensitive as passwords. If somebody has your token, they have access to your account, period. It's just as, not quite as strong, but it's pretty much as strong as storing a password. It's not quite as strong because tokens can be easily revoked, but and passwords can be easily changed, I guess. But we need to store these in a sensitive manner, which means storing hashes of these tokens. Because if somebody gets a database of tokens and they're not hashed, they're just out there in the open, well, they're going to use those tokens to masquerade as any user on your site, even though you're salting and hashing your passwords and doing everything you're supposed to there. If your tokens are in plain text, getting that database just compromised every user's account. And they can just be anybody on your site without ever knowing your password. They don't need to know your password to attack you if they have your token. So we're going to store hashes. And note that we don't really need salts for these things. You can add a salt if you want. But since the entropy is over 80 bits, you're going to generate them to be over 80 bits of entropy. There's really no need for a salt. It's just not necessary for these things. Too much entropy. No rainbow table in the world is going to attack an 80 bits of entropy. Not going to happen. So I think I talked through this multiple times. I don't think we need this slide. Just make sure there's nothing I missed. If the token isn't in your database, you know that this user is not authenticated. Typically, you would redirect them to your login page. If the cookie's not set at all, redirect to login page. Oh, I highlighted the wrong thing. Redirect them to the login page, and anything that needs to be secured needs to be locked behind authentication. Somebody tries to access a secured resource without a valid auth token, you would send them a 403 forbidden or some other, or redirect to the login or something to say, hey, you shouldn't be here. Don't serve them the content. And as mentioned, if somebody has access to your cookies, they have access to your auth token, and they can be you. So making sure you keep your cookies secure is very important. It's of critical import for these cookies. So all the stuff we talked about with cookies, the directives mainly, HTTP only is I believe the only requirement that I have in the homework doc to make sure these tokens are HTTP only. So somebody who injects JavaScript into your browser can't just access your cookies directly. They can try to access them some other way, and we would have the same site as strict and and secure. We would have those directives, but we won't have HTTPS until AO3. So if you're not doing AO3, I can't say, well, you can't do the other AOs. So I didn't add those as requirements. But cookie hijacking, very scary. So let's see if we cracked that hash. We should have it by now. Hey, there it is. So this code that had no idea what the original password was, it had the hash, the salted hash, mind you, and the salt. With enough time, you're going to break that password. Now, that doesn't mean I broke SHA-256. I didn't break the algorithm. The algorithm did everything it's supposed to do. It computed a whole bunch of hashes, lots and lots of hashes that I just checked. It did exactly what it's supposed to do. I did not reverse the hash. It is still acting as a one-way function, but I used it for its intended purpose and cracked that hash. Enough time, you're going to crack any hash. So if your password's strong enough, hopefully enough time means until the heat death of the universe, and then your password isn't ever going to get cracked. So that's the level of security we want. But if you have 8 characters, mix of upper and lowercase and everything, and you stick with I'm going to do the bare minimum, your password can be cracked pretty easy. My dumb, stupid code just did this with length 5. Now, it's quite a bit more to go all the way up to length 8, but if I let this run for weeks, I'd crack your password with my dumb code. So anybody running anything more sophisticated who's not using a bunch of messy Java and string concatenation in a loop and things like that are going to be able to do this a lot faster. Parallelize, I'm single-threaded here. A lot of things. If they're running on a GPU that can run 1,000 threads in parallel, bad stuff. Bad stuff's going to happen to you. I clicked the wrong one. I did. Open up an incognito tab. Oh, maybe I didn't. Did I? Is this Firefox? Did I know? Yeah, I think I did the right one the first time. All right, let's open up an incognito tab in Chrome. Oh, my brain. Congregate.com. I couldn't even think of the domain name. It's been a while. It's been probably exactly 1 semester since I visited this site, since I did this demo last time. So let's go to Congregate and play some games, right? So I'm going to inspect element. I'm going to go to application, and you can view all the cookies that are being used when you visit a site. Go to your application tab, and I have all these cookies. A lot of them. I just opened a brand new incognito tab, and look at all the cookies that are already set. Cookies are used constantly to track you as you move throughout the internet. And let's hit refresh, see if I got any extra cookies here. No, looks like not. But Twitter.com has some an entry for cookies here. So presumably they want to set some cookies. Maybe my browser's blocking it. I don't know. I don't know what's going on. But I expected to see some third-party... Oh, accept all cookies. Let's refresh. Notice how many cookies were set before I accepted cookies too. Like those banners are they're just there. But I have a lot of cookies set here. Let's go to another browser. Congregate.com. And I'm logged in. And level 21, yay. I'm going to go to inspect element. Make this bigger. I'm going to go to application. Here I do have some Twitter things. So maybe Twitter is being blocked because it's an incognito tab. I don't know. But Twitter is tracking me when I go to this site. I don't use Twitter, so it's not like they got me and they're, nope, they're just tracking me. It's fun going to sites and seeing how many places are tracking you. Let's see what else we got here. Twitter, Congregate, Twitter. All right, and what I have here are a few tokens right here, this Kong sec, which I believe shouldn't show up over here. And you as a user have full access to all of your cookies. Like we can look at the directives here. I have 2 cookies that are HTTP only, but HTTP only doesn't mean only HTTP. It means HTTP, and also you can go into your browser console and check them out and do whatever you want with them too. So we have HTTP only in this Kong sec for secure. What I'm going to do is grab this value. And over here, notice it's incognito. I'm not logged in and anything. What I'm going to do is add a new cookie, Kong _sec. Let me double check. Kong _secure. I'm going to add it with this value. I'm going to refresh the page. And I think there's one more, this SVD. I think I need this one too. Paste. So I just manipulated my own cookies. Refresh. Oh, you bastard. BID. The session. Let me get my congregate session, which should be set over here, because that's just a user session, not a auth session. And now I'm logged in as me. I didn't have to type in my username and password. I didn't have to compromise anybody's password. I just stole that auth token and a few other things. Congregate looks like they're doing a few other checks to make sure the session matches the auth token. But I grabbed those tokens, and I'm able to log in as me on a different browser without ever actually going through the login process. The server said, whoa, hey, that session ID and that auth token, yeah, you must be Jesse. You must be HeartLoadJL. And just treated my request as coming from HeartLoadJL. These are as sensitive as passwords. They can be used instead of passwords to authenticate once a token is issued. And these tokens usually last a long time. There are some sites, like this site, where I log in once and I forget I forget my password even. So this consec, it says session, but I should reverse engineer this and figure out exactly how this works. But some of these tokens, this one, 2041, it'll expire. 2024, these things will expire. Maybe consec must be generated each time based on one of these other tokens, but I always forget which one is which. But you can log in as somebody by having that token. So